So, hi everyone. Yeah, Rohit, can you move to next slide?
Sure.
Yeah, please. I jump to slide 3. Okay, so, hi everyone. So, have you ever wondered how we can make computing work even when our power source is as unpredictable as weather? So, well, that's where intermittent computing comes into play. So, it's a cool new approach that lets devices run on energy sources like solar cells or energy harvesters, even when the power isn't constant. So, think of it like powering through those annoying brownouts without skipping a beat. So, yeah, but of course. With this new way of doing things, we face some interesting challenges. We've got to make sure our computations keep chugging along smoothly and our data stays safe, even when the power blips out. So that's where the techniques like checkpoint-based execution and energy-aware programming come in handy. So, and these applications, like from batteryless IoT devices to wearable tech and embedded sensing systems, there's a whole world of possibilities opening up. So we are even experimenting with running AES 256 benchmarks on MSP432 under intermittent power, just to show off what's possible. So it's all about making computing more sustainable and energy efficient for those tricky environments where power is scarce. So can you move to next slide, slide 4?
Sure.
Okay, so now let's dive a bit deeper into MSP432 microcontroller. Picture this. It's got this neat analog to digital converter module that can handle single-ended analog inputs like a champ. But what really sets it apart is its flash memory, a whopping 256 KB of it. And get this, it's organized into two banks so we can read and execute operations simultaneously even during erase cycles. Why does this matter for intermittent computing, you ask? So, well, that flash memory is like a safety net. It hangs onto our data even when the power goes out, ensuring we can pick up right where we left off. And the way it's all mapped out with code here and peripherals there, it's all about making the most of what we have got to work with. So, yeah, you can move to slide 5.
Oops, sorry.
Yeah, so now let me introduce you to the PowerCast P2110 EVB board, our ticket to testing and developing intermittent computing systems. This baby is all about harvesting RF energy and turning it into usable power. Just imagine it takes those radio waves and converts them into DC power, storing it in a capacitor to give us that intermittent voltage we need. And why is this important? Well, because in the real world, energy isn't always available when we need it. Sometimes it's there, sometimes it's not. So just like with this board, and yeah. So and by simulating those conditions, we can fine-tune our intermittent computing techniques to work seamlessly with energy constrained devices. It's all about making sure our tech can thrive no matter the power situation. We can yeah, you can move to slide 6. So, all right, let's talk about setup. We have got our RF source, our trusty broadcast board, the MSP432 microcontroller, and a picoscope for keeping an eye on things. The powercast board is doing its thing, turning those RF waves into a nice steady voltage for MSP432 to work with. But here's the really cool part. We have set up this just-in-time logic that kicks in when the voltage starts to dip. It's like a safety net for computations. When the power is about to go out, we quickly stash away our progress in the flash memory, ready to pick up right where we left off when the juice starts flowing again. And of course, the picoscope is there to help us analyze and optimize our setup, making sure everything's running as smoothly as possible. Because when it comes to intermittent computing, every little bit of efficiency counts. So now let's dive into the code and the working, which Rohit is going to explain.
Sure. Thanks, Rohit. Um, I'll quickly go into the code now. Let me just navigate out of this. Okay, so yep. So this is our code, which is very similar to what we did for the third experiment, which was using AES for benchmarking. We are using the same program, which is AES, but we're using a smaller variant of it because only a byte can be written to flash at a time. And so the maximum number that can be written to flash is from 0 to 255, if we are strictly speaking about unsigned integers. So let's take a deep dive into the code. So the first few lines are all the basic includes that we use. And then we have our macros defined, which is the AES block type. And then we are defining three LEDs, which we are going to use for our experiment. We have the blue, green, and the red one. And then we have a button. So I'll explain the individual workings of these LEDs when we go further into the program. So for now, I've just defined macros for these three LEDs. And then since I'm using a button to start my encryption once it's over, so it's running in a while loop. And once the encryption is over, if I want to restart it again, I just press the button and then my encryption restarts. So then again, we are defining UART, which is just for, when I say it's just for testing purposes or debugging purposes. Right now, our board is not exactly connected to our laptop, which is like a continuous power source. So we need probably a UART to TTC converter or something like that to actually see what the output is. But for now, we are just going to ignore this UART in our code. And then tiny AES is what we are going to use as our programming benchmark, which is going to actually complete the encryption. And so Rohit has already explained to you the circuit as to how we are connecting things, right from the RF source to the power cast to the board. So let's do a deep dive into what the while loop says. Now, this is where the fun part starts. So calibration start is the memory location to which we are writing our data. And calibration start is a part of the flash memory. So Rohit just explained the memory diagram, and then this particular memory location is a part of the main flash memory. So there are particular memory locations to which you cannot write, and there are some locations to which you can write. So this thing can be selected from the user guide to just identify which is a safe memory location. And then since every memory location is divided into two banks, I mean, it would be a part of either bank 0 or bank 1, and then every bank is divided into 32 sectors. So this particular memory location is a part of bank 0 and sector 31. And then we have the keys and then the plain text, the ciphertext, which is exactly what we used in our last experiment. So that we already covered in our previous video. Now we have an array which keeps the count of the AES. So right now we are simulating a large piece of data with multiple data chunks. So whenever we complete the encryption of one data chunk, we store that particular variable in this array called AES count. And then this particular array or the value in this particular array is going to be written to that flash memory location. Now, as Rohit said, for just-in-time logic, we also need to calculate the value of the ADC because your power is not continuous. Your power is dampening over a certain period of time because it's essentially a capacitor that's getting charged and discharged. So it's an RC circuit, somewhat similar to an RC circuit. And then, so we have current ADC result, which stores the sampled result of the ADC, and then the normalized ADC result, which actually gives you a value between 0 to 3.3, which kind of helps you to identify what exactly is your voltage. Now, plain text, ciphertext is something which you've already seen. Key size is 256. SW state is my switch state, which is just to check whether if my button is pressed or not. Init AES is just initializing the AES. The LED init function is just initializing our LEDs. They're just setting them as outputs. Button one init is setting my button as an input that has to be sent to the program. Button one get input is a code wherein I'm checking whether if the button is pressed or not. Since it is a pull-up resistor, whenever I press the switch, the value that's returned by this particular function is 0. And so if not 0, if 1, so if it's pressed, then my return value is a switch press. And then I'm just returning that value. Then test encrypt is where my encrypt function is, which we treat as a black box for now. UART put char, UART puts, UART init are the same functions that we discussed in our second video, which was about UART. UART hello world. It's the same thing essentially. And then ADC init is something which is new. ADC init is something which we have not looked into before. So we are just initializing the ADC module. So the first two statements are, we just enable the module, and then we initialize the module with which divider we need to use. And these are like specific ADC configurations, which can be seen in the MSP432 example code. And then we have set as peripheral module function input pins. So P5.5 is the pin which I'm setting as my ADC pin, and that is the pin which is going to take the ADC output. Now I'll go to configure single sample mode. So this is something like I need to continuously monitor the ADC. So if this is false, then it's just going to give you a one single value of the ADC and just stop the module. But we need a continuous sampling, so it's true. And then this is just enabling the sample timer, which kind of gives you the ADC result. Now, since this is all, these are floating point values, so we are just initializing our FPU module, which is the floating point module. Then this is a particularly important piece of code for our particular program, because this is the exact checkpointing thing wherein you are writing data to the flash. And so an essential thing to understand while working with Flash is that Flash is a protected sector, because this thing is particularly staying on the board. So you need to first unprotect that sector, pass to it the bank and the sector to which you are writing this data, and then Flash before erasing it. If you want to write anything to Flash, you first need to erase the sector. So erase sector essentially erases that particular memory location. So by erase, we just mean that it overwrites any value which is there in that place and replaces it with all 1, 1, 1, 1, or F, 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 F. Program memory is the function which writes the data, which is in AES count to, which is define what is the size of the input. And then once we are done writing the data to Flash, we again protect that and unprotect the sector before writing anything to it. Now this is like we're done with all the peripheral functions, and now let's jump into the int main. So we just initialize the board, initialize LEDs, initialize AES. We have a variable value. Value is nothing but exactly which computation we are doing right now. So it's like our whole data is maybe 250 chunks of 16 bytes, which is our plain text. So whenever we complete one chunk, the value is 1, second chunk value is 2. So value is nothing but which chunk is exactly being processed at that particular time. And then flashed is something which is 0, but this technically indicates whether if something's already been flashed or not. So if something's already been written to Flash, this particular value is going to become 1. So essentially, it's just going to write it to Flash just once during every power cycle. So this is specifically for intermittent power, because if you do this for continuous power, then it's just going to be written to Flash once. So you need to disconnect the port, connect it again, and then your value is going to increment in the Flash. Now, these are just basic, not basic, but these are mandatory functions wherein you set the core voltage level and then set wait state. You need to show which particular flash bank you're using and then use these functions. And then we change the clock frequency to 12, something which you already done in UART. And then UART in it is, I mean, we're doing it now, but we don't really need UART in it. And then you're just using FPU in it, ADC in it. Now, line 200 and 201 is where you are reading the value that has been stored in calibration start. So every time power is removed for this program, it starts from the first point. And so whenever it hits this point, it reads the value that was stored in the flash in its previous iteration. So this is how you read the persistent value that was in the flash. Now you have while one. In while one, you have enable conversion and toggle conversion, which is just like start the ADC and give me the result. This particular thing is like once the ADC, if the ADC is busy, then it just moves in this while loop. Current ADC result is what gives you the sample value, which is stored at this particular memory location. And normalized ADC result is like, because your VCC is 3.3, so you need to have some value between 0 to 3.3, and that's what normalized ADC result gives you. Now, 250 is our threshold wherein we are representing the huge chunk of data. So while the value is less than 250, that's when this particular thing is running. So while value is less than 250, let me turn my blue LED low. So blue LED signifies the end of my encryption. When an encryption is going on, my blue LED is going to be turned off and my red LED is going to be turned on. So that's why it's high on pin red LED. Test encrypt is it's encrypting one chunk of data and then it's setting the red light to low. And then I'm incrementing the value by plus plus. So one chunk of data, red LED on, encrypted, red LED off, and increment the value. So now the next chunk. Now, if the value is equal to 250, we just break out of this. So when it hits 250, just break out of this loop. Now, inside the loop, this is the main part when we're actually achieving the just-in-time thing. So if the result is greater than 1.6, so this thing kind of requires some trial and error as to you need to check with the picoscope, what is the highest current the board is taking, what is the lowest current the board is taking, and then if my and when exactly my falling or when exactly my current is starting to fall. And so I need to stash my stuff in the flash before this starts falling, because as the voltage to your board goes on decreasing, it's kind of uncertain if thing is going to be safely stored in the flash. So we just ensure that we have sufficient voltage for things to be stored in the flash. And once they are stored in the flash, my flash becomes 1. So essentially, this just means that for every power cycle, this just stores it once. And then it turns the flash to 1. So even in the same power cycle, if we encounter into this again, my normalized UDC result, even though greater than 1.6, my flash value is now 1. So it's not going to write to flash. It's just going to stay as it is. So let's say my value is equal to 0. The value is equal to 1. It gets stored to flash, and then the value can become 1, 2, 3, 4, 5, or whatever it needs to be. But when the power is removed from the board, all of those future values are kind of lost. And then the next time the power turns on, we just get value 1. So essentially what we're looking at is 250 input power cycles to the board, and that's how you achieve the encryption. So you set the memory as the value, the what is the value in the value variable into AES count, and then you set the green LED on. So green LED on means that stuff is being written into flash, and then once the stuff is written into flash, the green LED turns low. So stuff is being written into flash, green LED is on, and then once this is done, the green LED is off. And once all of this thing is done, I'm setting the blue LED to on, so that means that my encryption's over, and my red LED to off. And then once my encryption's over, the code's just gonna move in this blue LED on thing. And then if I press my button, then it again turns the value to 0. So that's when my encryption starts again, because then I'm setting low to blue LED, and then it's gonna again go into this loop and start the value. So turn on the red LED. So this is the entire code as to how we achieve this particular just-in-time functionality. And we have attached this to the picoscope. Additionally, we can also view this from another screen. Let me just, where's this? Okay. And then pin. I don't know if I can turn this on. Okay, that's the maximum this can go to. And now let me just start the video to this. Yeah. So this is the board. And then as you can see, the red LED is turned on for every, let's say, one positive power cycle. And then the green LED flashing is, sorry, the green LED flashing indicates that it's being written into flash. So I just started the code now, and then it's gonna take like a lot of time for it to be executed, because one power cycle is just one write to flash. So essentially it's 250 power cycles until this code kind of depletes. So let's just check on the picoscope as to how our power output is. So let me just minimize this and go to picoscope. Stop video. And now moving on to the picoscope. So on the first below probe, or the scope 2, I have my input power. And then on the above probe, I have the encryptions. So you can see, let me just pause this one. So if it's kind of running, so I just pause this, and then you can see that the positive width is 1.174 seconds. And then if I just do a measurement for the second code to just get the entire cycle time, then it is 2.143 seconds. So every 2.143 seconds, just one value is being written into Flash, and then we have 250 such values. So it's essentially 250 into 2.143. Oh, sorry. Oh, 250. Oh, my bad. Why isn't the ideally on? So it's essentially 250 in what the? Oh, I haven't started the numlock. 250 into 2.143. So that's essentially 535 seconds for the entire program to run, which kind of just takes around 25 seconds on continuous power. So you can see that this is like 3.3, this is 3.3, and then this is where my value falls to 1.6. And you can see that this particular edge, can I just zoom in on this? Oh no, it's distorting it. But as far as my power is above 1.6, this is the encryption that's happening. But since this thing is kind of directly proportional to the distance between my RF source and the power cast module, if I increase the distance, then this particular power cycle, like the positive time, goes on decreasing. So the minimum it can go up to is 100 milliseconds. And in the last experiment, we deduced that 20 milliseconds is what it takes for one chunk to get encrypted. So keeping that in mind, we have just saved one flash state per positive cycle. I mean, in this case, you can argue that all of these are redundant power cycles because these are anyways going to be diminished. So it can take much, much lesser time than 535 seconds. But in our case, we want to do this with the worst possible or the maximum possible distance between the source and the power cast. So taking that into consideration, our code is writing just one memory location into this place. And so this thing is going to run for around 9 more minutes. So, well, maybe I can pause the video, or we could just attach a screenshot as to once this thing is done, but maybe. So Rohit, when did we start this? Was it like 8 or 7 minutes ago?
Um, yeah, most probably it's maybe six or seven.
Okay, because I don't exactly know when it's being done, but
Yeah,
what
we
I
can,
know is that once this thing stops, that's when our encryption's over,
we
because
can,
when the red
yeah,
LED turns off, that's a signal that our encryption's done. So
we can attach a screenshot or something in the end. Like,
yeah, or we just need to wait once it's over. I don't know.
mm, yep, we'll attach a screenshot, so that should be efficient for
Yeah, I hope it's
in the
oh
folder the
oh
way we are going to put the
oh it's
video.
over. So
Yeah,
so
it's great.
so this like signifies the end of our encryption, because now the red LED is no longer being turned on, and then we're just having intermittent power supplied to it. And then if I want to start my encryption again, I just press on the switch. And so I'll just press the switch here, and then my encryption starts again. So let's see, I have pressed my switch, and yeah, that's where my encryption starts again. So this is kind of like a gibberish thing. But now my encryption has started again, and it's gonna go for 535 more seconds until it gets over. So I mean, but it pretty much tells the gist of how we are saving a particular value. And then essentially before we run out of power, I am stashing everything to flash. And so 1.6 is because the moment it starts falling is somewhere between 1.6 and 1.56. But this particular thing is like very unreliable for storing anything to flash because your power is consistently decreasing, and so is the performance of your processor. So that was it. That was about intermittent computing. And yeah, thank you. Thank you, Rohit.
Yeah, thank you.